Hello everyone, today we're going to look at usaco-training beef McNuggets. So in this problem, Farmer Brown is basically selling some beef McNuggets, and basically what he has is some boxes containing some amount of McNuggets. So for example, if he has these McNuggets in boxes of 3, 6, and 10, he cannot satisfy a customer who wants one McNugget, 2, 4, 5, 7, 8, 11, 14, or 17. So basically, like, he will not be able to provide this specific amount of McNuggets. Okay, so what we're going to do is that we're going to be given these these n types of McNuggets. And okay, so then we're going to print out the largest um, impossible number such that it's not larger than 2 million. All right, so in this case, if we have 3 types of packaging options and the types are 3, 6, and 10, these are the only types or only amounts of McNuggets that we cannot provide, and the maximum would be 17. So we would just print out 17 on one line. All right. So right now, so we have our n. All right. So let's call our a integers or our n integers a1, a2, a3, a4. So dot dot dot. Let's call this an. All right. So let us call some number. So let's just say we can make some kind of x. Okay, so then this is going to be some kind of coefficient that goes with 1, some kind of coefficient that goes with 2, some kind of coefficient that goes with 3, 4, and dot dot dot, some kind of coefficient that goes with n. So then you can, and where ci is greater or equal to 0, and ci is an integer. Right, so let us define this. And what we can do first is that let's just solve this problem if we only have two, if n is equal to 2. So let's consider if n is equal to 2. Then we're just going to have a1 and a2. All right, so then for a given x, we may have a c1 and c2. Right, so first thing that we want to do is that we want to determine if there's going to be an infinite amount of what do you call it, of like amounts that we can't make. So what we're given over here is that over here, if basically if there's no bound to the largest numbers, then we're just going to print 0. So the first thing that we're going to do is to basically to eliminate this case. All right. So then basically we want to determine. Okay, 1 second. All right. So we want to determine if there is no bound. And the case that this happens is if the greatest common divisor of a1 and a2 is not equal to 1. So when it's not equal to 1, for example, you can have something like 4 and 6. So in this case, it's pretty obvious that you cannot make any odd amount, which means that so let me try to prove this. Okay, so right now you have your GCD of 4 and 6 equal to 2. So this means that you can basically only make the kind of the jumps of 2. So which means over here in this case, right now you have this, let's call our GCD equal to G, let's just say. So this is going to be plus G at most, okay? So you're always only be able to making these plus G jumps, all right? Or similar, okay? So in this case, you may just be jumping like this many, or you might be jumping some other case. But then, if you notice that you can only jump plus G every time, then it means that you cannot achieve the amounts that are in between G and like 2G, for example. So then now we can basically kind of eliminate this case where GCD, or this case where there's no bound. All right, so now we got that case. So now let me just introduce some kind of another idea. So given these numbers, so for example, we have A1 and A2. So we can use these numbers to kind of create a knapsack, okay? So we can define DPI, whether it's going to be whether we can create the sum of I. So then to create transitions, it would just be, our transitions would be DPI would be DPI minus AI, or AJ, let's actually call this AJ. So if this, or DPI minus, this is actually, let me erase that. Alright, so let's delete that. So over here, this is going to be, since we only can use A1 or A2, it should be A1 and A2. So if either of these are true, then we can make DP of that. So then, right now in this problem, our upper bound is like 2 times 10 to the 9th, which is pretty large. So you cannot like store some DP array that is the size of this upper bound. But let's just say that maybe our upper bound is going to be like something like this. Okay, so let's just say we're assuming this. So now we can apply this DP transition, and then now to find our answer, we just basically loop from this thing to 1. So then if we cannot create, so if not dp of I, then our answer is equal to I, and we can just break or something. So that's only if our upper bound is pretty small. Okay, but in reality, given in the problem statement, whoops. Okay, so given in the problem statement, our upper bound can be pretty large. But actually, even though it says that our upper bound is this many, it actually cannot be that much. So let's actually take a look at something. Okay, so over here, according to the chicken McNugget theorem, it says that for any two relatively prime positive integers, m and n, the greatest integer that cannot be written in the form of am plus bn for non-negative integers ab is mn minus m minus n. Okay, so let's take a look back here. Okay, so right now, again, we have two numbers. Okay, so we have a1 and a2. All right, so let's look over here. So right now we're trying to find two integers, c1 and c2, such that both of these numbers are basically non-negative integers. Exactly what is fitting in the proof, or in the like claim or something. So now, right now we know that AI has to be less than or equal to 256. 56. So we're going to, so right now, let's assume that A1 and A2 are relatively prime. Okay. So then, if GCD A1 A2 is equal to 1, so then this means they're relatively prime. So if they are, then our basically our answer is just going to be bounded by the product minus basically minus their sum basically. So minus A1 plus A2. All right. So then if this is basically our bound, then the maximum, then our upper bound, as I wrote over here, it's not going to be this. Instead, it's going to be around something like 256 squared, which is a pretty small number. All right, so now we know that for two numbers, for if we have two numbers, then their upper bound would be at most this. All right. Okay, but we have at most n numbers, so we might have like n is about 10, so we might have like exactly 10 values. All right, so let's get over here. Okay, so again, so now we want to like try to we want to prove that the upper bound. So we want to prove that the upper bound is equal to 256 squared. Okay, so right now, let's consider that we have to take at least two numbers or two distinct numbers. Okay, so if we take at least two distinct numbers, then it means that that our upper bound again would be this. And this is because if we take two numbers exactly, then our upper bound would be this. It's shown in the proof. It's actually pretty complicated. So then if we take three numbers, um, the highest value that cannot be that cannot be represented by this would basically only decrease because let's just say right now, okay, so we have two numbers. We can let's call this A, let's call this B. So we know that this is our upper bound. So now we have three numbers, okay? So then if we have these three numbers, we can basically choose, let's just say we can also choose to use just these two numbers. So then our upper bound would be this. But then if we also choose to add this number, our upper bound would only decrease since by adding a different number where basically we have more choices, which results in more possible x. Okay, so we now know that for 2 plus numbers, or basically if we choose 2 or more, then our upper bound is going to be this. But then there's another case. Let's just say, oh, wait, maybe we can just use one number. All right, so if you have one number, then there's not going to be an upper bound, meaning that you won't find an answer. Okay, so let's see. Okay, so if you choose one number, all right, so for example, if you have A1 equal to 5, okay, so if you choose this, then again, it's going to look something like this, where we're going to make this jump, okay, and if you make this kind of jumps, then as you can see, the red portions are going to be left out, meaning that it's you're not going to find an answer here. So let's kind of summarize that. Oh yeah, so one more thing actually. So right now, before we already determined if there is no bound on two integers. Okay. So now, similarly, now we have n integers. Okay. So then, our thing is that if GCD of A1 a2 dot 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 an. If this is equal to, or if this is not equal to 1, then our answer is equal to 0. All right. Otherwise, our upper bound is going to be equal to basically this. So then our size of our dp would just be this many amount. And this would both fit in memory and time. All right, so now if you have our dp, we can just perform this the knapsack that the knapsack that I mentioned here. So now we filled out our dp values, and then finally we loop from our upper bound, which is now 256 squared. If we find something that's not right, our answer is equal to I and then we break. All right, so let's get coding. Okay, so over here, all right, so let's, this is other, okay, so let's get nuggets dot, let's open that. Whoops, all right, so over here we have this nuggets, all right, okay, so over here, insert my template. So we have n, read n. We have a, the values, so it's going to be at most 10. So for 0 to n, it's going to read that. So now we want to basically determine if our answer is going to be 0. So it's called G going to be our GCD of every element. So we're going to take the GCD of G and A of I. So then if G is not equal to 1, then we're just going to print out 0, and we can just end our program here. Otherwise, we know our upper bound is going to be 256 squared. So let's call our dp. So let's call this our upper bound is going to be 200 and let's just call this 260 squared. So this is going to be so over here, what you have is that you know that you can make something with 0 values, okay? Or you can make a sum of 0 with nothing. So then you just loop through from 1 to up. Then we're going to loop through each element that we have. So if I is greater than or equal to aj, and dp of I minus a of j is equal to 1, so meaning that you can make this value, then dp of I will be equal to 1. All right, so that's just a basic knapsack, and now we need to calculate our answer. So we're just going to loop through up minus 1 to 0. So if not dp of I, then we're going to printf that integer, and we're just going to return 0. All right, so and over here, this case shouldn't happen, so I'm just going to make an assertion here. So let's run that. So we have these numbers. All right, so 17, that's correct. Let's open nuggets. Nuggets to out, right? Let's CDO. All right, so this is nuggets. All right, okay, so remember one thing. So in C++11, this should actually be So this is nuggets. Let's submit that. Alright. Ooh, okay. Okay, so assertion 0. So maybe it looks like okay, so over here we get that GCD is equal to 1. Oh, and the element is 1. So okay. Okay, so I kind of see what's going on. So what's happening is that we're not getting anything. So we could just change this, give it a 0 instead, meaning that since this is basically the upper bound, if you cannot find anything, then it means that like if you cannot find anything, that since it's the upper bound, then it means that you cannot find anything from this to infinity. All right, what's the problem here? Oh, okay. So I think you can just remove this GCD as well. All right, so since that nuggets, okay, so oh my output. Oh, okay. Okay, so I should actually solve that out. So let's get over here. So remember what I said, that the upper bound was going to be around this much, okay? So then what's going to happen is that, okay, so you have two integers, 256 and something like 255, okay? So since these two are like relatively prime, you may want to like consider this. So over here, this is not the actual upper bound. You're going to have something like n times m minus n minus m. So then this is going to be 256 times 255 minus 256 minus 255. All right, let me use a calculator. Let's get over here. We have 256 times 255 minus 256 minus 255. This is going to give us this number, so this is going to be the upper bound. So we're just going to do this plus 1. All right, so let's submit that. Nuggets. All right. My output, their output. Okay. I guess we still. Oh yeah. Okay. I shouldn't have removed the GCD case, since it actually does help the program as well. Okay. All right. Because means even though maybe that you can skip these numbers, the GCD is something that's going to hold it behind. Oh, okay. So everything is correct. Thank you for watching. If you have any questions, feel free to leave them in the comment section below. Bye.